Although this is not a building structure, we are going to design it under Chapter 12 as a non-building structure that is similar to buildings. Additionally, the cables are a flexible, self-dampening structure. We are not worried about the effects of seismic activity on the structural integrity of the walkway because of its dynamic nature and its flexible nature. Think about a building with a glass facade that could break under much smaller deflections than what the cables experience. So this simplified analysis that I'm going to go through is to calculate the seismic base shear on the abutments, and just the abutments. However, in an active seismic zone where seismic loading is a concern, the cables potentially could actually amplify the force on the abutments and should be modeled with the entire structure. So this analysis will also ignore the drift and P delta effects, so effects of increased loading, increased moment because of deflection or drift of the structure, amplifications due to any torsional irregularity, and more. And because of the general non-standard nature of this structure, it really should be analyzed with computer software using dynamic time history analysis or modal response analysis. And these are some things we've done in the SAP 2000 software, and is just a more efficient way to do a useful analysis of the entire bridge. However, what I'll go through here is a pretty standard design procedure. It'll get you familiar with the terms and how to think about calculating seismic loads on your structure. So we'll start with Chapter 12, Table 12.2-1, Design Coefficients for the Equivalent Lateral Force Procedure. So remember, we are just considering the abutments here, which the main force resisting system is through bearing walls. So we'll read our response modification factor, overstrength factor, and deflection amplification factor, as well as where to go to find reinforcement detailing and general detailing of the structure. We can read these values from this table. And remember, we're using these values to turn our ground motions into a static analysis, or static loads onto the structure. So it doesn't consider the inertia of the structure. So we use these factors in conjunction with the weight and acceleration in order to estimate forces. And a quick note on overstrength. Overstrength is used to control the yielding of a structure during a seismic loading event. It's used to beef up some of the other structural elements so that there is no weak link in the seismic force resisting system, and the intended element, usually a brace in a steel structure, will actually fail, and we can know what to expect out of that failure. And it's generally required when the response modification factor is greater than 3. And this is usually ends up being the case for more ductile steel buildings. If it's starting to hail outside, you can hear that. So next, in section 12.3.4, we're going to take our redundancy factor for seismic design category D as 1.3. And then in section 12.4, we'll begin to discuss load effects and combinations. So it says in this section, seismic load effects are the axial, shear, and flexural member forces resulting from the application of horizontal and vertical seismic forces. So seismic load effects are reported using the variable E. For ASD, you can see the primary load factor is 0.7. For LRFD, it is 1.0. The blue starred combinations should use an E value that is a positive combination of the horizontal, EH, and vertical, EV seismic loads. And notice that the magenta starred combinations here use a reduced dead load and should be used with EH minus EV to expose potential uplift or overturning concerns at the soil structure interface. The colored combinations written below show how the vertical and horizontal loads should be applied in the combination. So here we have for ASD and LRFD. Now I'm going to pause here, and in the next lecture, we'll dive into 12.4.2.1, the horizontal seismic load effect.